Yeah, today we shall discuss about amplifiers. It is an introduction and classification of amplifiers. As I mentioned earlier, an amplifier is a two-port device. It has an input port and an output port. The input port takes signal from a signal source, and at the output port it gives an amplified signal. The signal may be amplified in voltage or current or both. So there would be some power gain when you use an amplifier for the input signal. So please look at this diagram. So the amplifier has an input port here, and we apply an input to the input port, and we get an output at the output port. And to the input port, we feed a signal from a signal source at the input port, and the output can be used to drive a load resistance RL typically. And as I mentioned, this input signal can be a voltage signal or a current signal. And before going into the details of these amplifiers, let me discuss about the classification of the amplifiers. There are different means by which the amplifiers can be classified. And one way of doing it, or one appropriate way of doing it, is by means of the signal strength. So by means of signal strength, we have small signal amplifiers and large signal amplifiers as the classification. Small signal amplifiers and large signal amplifiers. As the name indicates, the small signal amplifiers are those amplifiers which take small signals as input, and the large signal amplifiers, on the other hand, take large signals as the input and gives you further large signals at the output. For instance, a microphone picks voice signals, and the voice signals, the strength of the voice signal is of the order of, or the amplitude of the voice signal is of the order of millivolts. It's a small signal. And then we amplify such microphone signals through an amplifier, a small signal amplifier, and bring its output level, voltage level, to a high voltage that is of the order of a few volts. Now, for applications like in a public addressing system, you need hundreds of watts of output. So then only a large gathering can be, a big auditorium can be powered with audio signal, amplified audio signal. Hence, you need further power amplification of this input signal. Here it is millivolts, and it is of the order of volts at the output of the small signal amplifier. And since the output is large here, the signal is large here, it's a large signal amplifier. Further, we pass the signal through power amplifiers or large signal amplifiers. Then the output is further large, it may be hundreds of volts at its output, and this can be used to drive several loudspeakers connected to the amplifiers. So in a particular amplification application, you may have small signal amplifiers as well as large signal amplifiers. So depending on the application, the configuration varies. Hence, there are small signal amplifiers and large signal amplifiers. As I mentioned here, small signal amplifiers take signals which are of the order of millivolts and microvolts and give sufficiently high outputs, whereas the large signal amplifiers use volts or hundreds of volts at its input, or volts or tens of volts at its input, and gives you a much higher voltage at its output. I am referring to the alternating signals not the DC supply. Okay, since an amplifier is typically used for amplifying the amplitude of small signals to a large amplitudes, where the shape is retained but the amplitude is scaled, or you get some gain in the amplitude. So this is one kind of classification based on the signal amplitudes. There are other kinds of uh, classifications possible, and one other classification which is important in our context will be discussed a little later. Now, coming to the sources which are used as the input sources to the amplifiers, we have different kinds of input sources. Some sources give you voltage as the signal. So voltage sources, such sources are known as voltage sources. So voltage sources give you the voltage as a voltage signal as a function of time. The voltage may be in millivolts or volts. Whereas current sources give you current as a function of time. Please note that if you have a voltage source and apply a resistance across it, or connect a resistance to the voltage source, you will find that the current flowing will be that voltage source voltage Vt divided by resistance R. Therefore, a voltage source can be converted to a voltage signal can be converted to a current signal. There is no doubt about it. Similarly, a current signal can be converted to a voltage signal by passing the current through a resistance. But depending on the characteristics of the source, so we classify them as voltage sources and current sources. So let us discuss in detail about what these are. Say you have a voltage source which produces a time varying voltage as the signal. Then this voltage, what we mean by a voltage source is when we connect a load resistance and vary the load resistance because of some other reason, vary this load resistance, this voltage should not change. For all practical purposes, this voltage should be constant, whether you connect a 1 kilo ohm resistance or 10 kilo ohm resistance or a 100 kilo ohm resistance. Or for that matter, even when you open circuit it and measure the voltage, that voltage should be the same even when a load is there and when a load is not there. We have sources like thermocouples. A thermocouple is a transducer which converts a temperature signal into a voltage signal. If you want to measure the temperature of a furnace, then we use a thermocouple. At the output of the thermocouple, it gives a voltage which is proportional to the temperature. So if the temperature is varying, the voltage at the output of the thermocouple is time varying. Okay, so such sources are voltage sources because the output voltage is almost independent of the load resistance you connect to it. So when it doesn't change with load resistance, it means that it is a voltage source, because when you apply a supply over here to the resistance, the current varies depending on the load resistance, but the voltage remains constant. But in practice, what happens to such voltage sources? Do you expect, say I'm taking the example of a constant voltage source. So this is the voltage of a voltage source and this is the current you draw through it. With current drawn, do you expect the voltage to remain at a constant level with practical sources? So typically the current, the voltage drops with the current drawn through it. If you connect a small resistance, the voltage drops to some extent. If the voltage is, if the resistance is large, the voltage is large. So the voltage of the voltage source is governed by this kind of an equation. When current is 0, it is V, and when current is high, it falls to some extent. So in which case, such voltage sources can be, ideally, if it is an ideal voltage source, the voltage should remain constant, like this. Hence, such practical voltage sources can be represented by an ideal voltage source in series with some source resistance. Now, through an external load resistance, if you draw some current through it, what is the output voltage here? Or if I call it as, this is VST, source voltage, ideal source voltage, and this is the voltage VIT. How does VIT depend on VST with I? So naturally, VIT is VST minus RS into IT. I is also a function of time, naturally because the voltage is a time varying voltage, and hence the current also would be a time varying current. Now please note that this equation is governed by this characteristics. This equation represents, so this characteristics. For 0 current, VIT is the terminal voltage here, VIT is equal to the VST itself. And with current drawn, so this is, the VIT is going to be less than VST. So this is a straight line equation with slope equal to minus RS. So a practical source like this can be represented by an ideal voltage source in series with a source resistance. If the source resistance is 0, it is very closely equal to an ideal voltage source. So typically voltage sources exhibit some amount of source resistance. That is true even with your main supply. When you turn on a water heater draws a large amount of current from the mains. You will find that all appliances like a bulb connected to the same supply, so exhibits some drop in the intensity, light intensity, because of a fall in the voltage. So that is because of because you're drawing a huge amount of current through the heater. So such sources as voltage source, voltage sources where the source resistance is relatively small compared to the load resistance, then it can be a source can be treated as a voltage source. On the other hand, you have some sources which can be treated as current sources, because the current from the source is independent of the load resistance. So here is a current source IT, and the current that flows out of the source is independent of the load resistance that is connected to it. Even if you vary this load resistance, if the current remains constant, then you call it as a current source. Please note that if it is a voltage source, if you vary the load resistance, does the current remain constant? So current is equal to voltage divided by the load resistance. Current varies a lot. So it cannot work like a current source. Whereas in a current source, the current is almost independent of the load resistance. An example for such sources is a an LED, or no, not an LED. So this is a photodiode. A photodiode can be used as an example for a current source. A photodiode, the current output, current passing through the diode is proportional to, so the light, so that is impinging on the diode. Current is proportional to the light intensity and not the load resistance. Well, the voltage is proportional to the current that flows when you pass it to a load resistance. That is a different matter, but the current is almost independent of load resistance, and that is only proportional to the light intensity. Hence, a photodiode can be treated as a current source. Now, when you look at the practical current sources, you find that the current doesn't remain constant. This is current. So current doesn't remain constant, and depending on the load resistance, the current falls. If the load resistance increases, then the current falls. If the load resistance is infinity, that means if you open circuit here, for the same current to flow through, if the current has to remain constant, how much should be the voltage drop? So voltage would be infinity. When the load resistance is infinity, if you want the source to drive the same amount of current through it, the resistance should be, the voltage should be infinity to drive the constant current through an infinite resistance. So no source can give you infinite voltage in its output. Therefore, with increased load resistance, the current falls. Hence, such practical sources, current sources, can be represented by an ideal current source in parallel with a source resistance. In parallel with a large source resistance. So please note that the current characteristics here. So the current I drops with RL in this fashion. So then when the terminal current going out of the terminals of this source, this is a practical source, behaves in this fashion, it is obvious that there is a parallel resistance Rs inside. So what is the slope of this characteristics? This characteristics slope is minus 1 by RL. And please note that the current drops only when you have a parallel resistance like this. If this is IST and this is IT, IT is equal to IST into RS by RS plus RL. So IT is inversely proportional to RL here. So IT is inversely proportional. With increased RL, IT decreases. Therefore, so this kind of characteristics can be obtained in this fashion. To get this kind of characteristics, you can use this kind of a model for a practical source. Well, when RS is much larger than, in this case RS should be much larger than RL. Otherwise what happens, if RS is smaller than RL, then what happens is this current appreciably changes with changing RL. If this is of the order of 100 kilo ohms and this is 1 kilo ohm, the current flowing through this and the current flowing through this are in the ratio of 100:1. Now if the resistance drops to 500 ohms, how much change would you expect here? How much change would you expect if this current is say 1 milliampere? So then the same 1 milliampere will flow through. The ratio is 200:1. So this current which flows through this would be reduced to half. That current is anyway negligible. So the change in this current is negligibly small when this is of the order of 1 kilo ohms and this is of the order of 100 kilo ohms. Even if you make it 2 kilo ohms, then this current won't change much. And when this current is constant, when this current is not changing much, this current is also not changing much. Hence, so it can be treated as a current source when RS is much larger than RL. Any questions on a voltage source and a current source? Questions? If there are no questions, I'll proceed further with another classification of amplifiers. So for amplifiers, the input signals can be current signals or voltage signals. And similarly, and the output, an amplifier may have two. Please note that input signals can be current or voltage. Now the amplifier gives you amplified current or voltage. So these are used to drive further circuit or a load. The amplified output in the public address system, the amplified output is used to drive a loudspeaker. So as far as the loudspeaker is concerned, so this amplifier is a source. So this is a source as far as the loudspeaker is concerned. Therefore, the amplifier also acts like a source. And depending on the application and depending on the particular load, you may need a voltage signal, amplified voltage signal, or amplified current signals to drive the loads, depending on the application. Hence, an amplifier also needs to give either a voltage signal at its output or a current signal at its output. Sometimes the input signal may be voltage and output signal may be voltage, in which case the amplifier is known as a voltage amplifier. And if the input signal is a voltage and output signal is a current, so the amplifier is known as a transconductance amplifier, because input is voltage and output is current. The gain of the amplifier in that case is current divided by voltage, which has the units of an admittance. Hence, it is known as a transadmittance amplifier. So by this classification, you have different combinations possible, and let me give you that classification. If the input signal is a voltage and the output signal is also a voltage, let me call it as VIT input, I indicates input, and let me call it as V0T, O indicates output. Then the gain of the amplifier is defined as the output voltage divided by the input voltage. It's naturally. If it is amplifying by 10 times, means output is 10 times the input. So that is defined as the ratio between the output and input is defined as the gain. Therefore, the gain, that means the transfer ratio between the output and input, is V0T divided by VIT. And this has no units. This has no units. and so this can be given as G, can be used as the symbol to indicate gain, and the amplifier type is a voltage amplifier. Now, if the input is current and the output is voltage, that means this is IIT and this is V naught T. The gain, the transfer ratio between the output and input has units of impedance. In which case it is known as a trans impedance or trans resistance amplifier. Now, if the input is a voltage signal VIT and the output is a current signal IOT, then the transfer ratio, the gain between the output quantity and input quantity, has units of admittance because it is IOT divided by VIT. And such amplifier is known as a trans admittance amplifier. And if the amplifier is working at low frequencies, so this ratio is real in nature, then it can be called as a transconductance amplifier, because an amplifier has capacitances in it, junction capacitances and circuit capacitances, etc. Because of which reason, in general, these ratios are complex. At low frequencies, however, so they can be approximated to be real quantities. Hence, they can be trans resistance amplifier and trans conductance amplifier rather than trans impedance and trans impedance amplifiers. Similarly, when the input signal is a current signal and it is IIT, and the output signal is also a current signal IOT, then the transfer ratio has no units, and such amplifiers are known as current amplifiers. So this is the classification based on the nature of the input and output signals rather than the strength of the signals. Earlier classification regarding large signal and small signal amplifiers, the point we considered was, or the classification measure we have considered was the signal strength. Whereas here it is the nature of the input and output signals, whether it is voltage or current. Extend that. Now let us take the case of a voltage amplifier and see what happens when you apply voltage sources and get an amplified output, and then when you use it to drive a load resistance. Now an amplifier it takes an input voltage VIT. For example, a voltage source takes an input voltage VIT, and under open circuit conditions it gives you a voltage source voltage VOT. Okay. As an example, if this is a 1 volt sinusoid, output may be a 10 volt sinusoid at the same frequency and same phase. In which case, the amplifier acts like just a multiplication by 10. So VOT is 10 times VIT, or in general, VOT is some gain G times VIT. So, if how do you represent this? as far as the output is concerned, it acts like a voltage source with voltage equal to G times VIT. Therefore, in the strict sense, you can represent it, model it as a voltage source. At the output, you can model it as a voltage source. With the voltage source amplitude as G times VIT. It is a voltage dependent voltage source. The output voltage depends on the input voltage. Hence, this amplifier, as far as output is concerned, this amplifier can be modeled in this form. Ideally, it can be modeled in this form. But when you connect a load resistance, so to this, what do you find? Do you find the output voltage to remain constant at VOT independent of RL? So you expect, so if you short circuit it, for instance, you expect the output voltage to be 0 because it's a practical amplifier. It's not an ideal amplifier. So you will find that the terminal voltage V naught T is, drops from GVIT. Hence, the output side can be modeled in this fashion. So this is acting like a voltage source. It's not an ideal voltage source. Therefore, it can be modeled in this fashion. So output side of the amplifier can be modeled like this. So it exhibits, it acts like a practical voltage source whose output voltage drops from GVIT. When it is open circuited here, the output voltage is GVIT. And with some load connected, and if the resistance is small, the VOT drops from GVIT. So that's because it acts like a practical voltage source. That means it has a series equivalent resistance here. So let us call it as R0. The R0 is used here, or RO is used here to indicate that as far as amplifier is concerned, it's the resistance in the output. Okay? Hence, the output side of the amplifier can be modeled in this form. Now, so let us look at the input side. So there can be a practical voltage source which is applied to this. So with the source voltage being VST, and the source may have some source resistance RS, because all sources are practical sources, they are not ideal. And when you connect the amplifier to the source, do you expect VIT to be equal to VST? Not really, because the amplifier loads the voltage source. That means it has some, it acts like some resistance being connected to the source. That means it draws some current from the voltage source. And because of this current drawing, so this voltage VIT is going to be smaller than VST because of the equivalent series resistance. Now, how much does it drop from VST? Depends on what? It naturally depends on how much current is drawn from the source. And how much current is being drawn naturally depends on how much does the amplifier load the source. Therefore, as far as the input is concerned, input side is concerned, the amplifier acts like some load with some load resistance to the input source. Hence, amplifiers on the input side can be modeled as a resistance whose value which can be indicated by Ri. I indicates input side. So an amplifier typically exhibits some input impedance Ri. In general, it is impedance, and it exhibits some open circuit voltage gain G, That means given the input voltage, the output voltage will be G times that input voltage, and that voltage changes with load resistance. That means it exhibits some output impedance. Okay. Now what is Ri here? Ri is therefore the input impedance. How do you find out? If you apply some 1 volt signal at the input or some VIT at the input, you observe some IIT as the current flowing inside, then Ri is VIT divided by IIT, the input voltage divided by the input current. Then what about the gain G? How do you determine gain G if an amplifier is given to you? Apply an input signal VIT, open circuit it, and measure the output voltage. Under open circuit, what is the output voltage? Is going to be V0T. Therefore, the output voltage under open circuit divided by the input voltage under open circuit gives you G. What about R0? R0 is the impedance looking into these terminals, or the resistance exhibited across these two terminals when this voltage is 0. That means when this is a short circuit, R0 is the impedance appearing between these two terminals. For this voltage to be 0, input side has to be short circuited. If you short circuit the input side, then this is 0, means this is a short circuit, and if you measure the output impedance here, so that is equal to R0. So if you are given an amplifier and if you are asked to find out how much is R0, what you have to do is short circuit the input to make this 0, then measure the impedance across it. How do you measure the input across it? Apply a voltage source, find the current that flows inside, so that voltage divided by the current flowing into the output terminals gives you R0. So R0 is the applied voltage at output V0T, it's an external voltage V0T divided by the input current that flows into the output terminals when input is short circuited. Is it clear? When the input is short circuited, the impedance looking into the output terminals, that is R0. Now once these three parameters of an amplifier are given, it means everything of the amplifier is given. It means that everything of the amplifier is given. Under any voltage, for any kind of voltage source, you can determine what kind of loading it offers, and then what kind of voltage that appears across this when VST is given, and when you connect a load resistance, how much of output voltage is obtained. Shall we determine about what is the overall voltage gain of this stage? Let us determine what is the overall voltage gain you are getting, because the voltage amplifier. Is it going to be equal to G? That means output voltage V0 by Vs. Is it going to be equal to G? Not really, because there is some attenuation here. VIT is going to be less than VST. By what ratio? Because VST gets divided between Ri and Rs. So VIT is a fraction of VST. And the output voltage is not GVI. Output voltage is again going to be is getting divided between RL and R0. So it is output voltage is a fraction of GVIT. Hence, output voltage V0 to VST ratio is going to be less than G. So let us mathematically analyze this problem. Now, under open circuit conditions, if VIT is the when the output is open circuited, what is the voltage gain V0 we will get? When the output is open circuited, the output voltage V0 is equal to GVIT. Input voltage is VIT. Therefore, the amplifier acts like an amplifier with gain equal to G. Right? When you consider the input voltage of the amplifier and output of the amplifier under open circuit. Now, if you are interested to express it in terms of VST, what is VST? If I open circuit the source terminals, whatever is the voltage that appears across the terminals, that is the source voltage. When it is not loaded, whatever is the voltage, that is the open circuit voltage of the source. So if you are interested in representing the gain in terms of that open circuit voltage of the source, because that is the standard, that is what is available to you. When nothing about the load is given, what is given to you? What is known to you? Whatever is the voltage it gives under open circuit conditions, that is the one. Now, if suddenly something is connected, it's going to drop. So let us express it in terms of this VST. So now on the input side, VIT is going to be VST into Ri by Rs plus Ri. Therefore, it is a ratio. It's less than 1. And on the output side, VOT, momental load is connected. So it's going to be VOT is going to be less than GVIT by what quantity? By this quantity, RL by RL plus R naught. Now, if we are interested in the overall gain of the amplifier in terms of the open circuit input voltage source or the ideal voltage source voltage, the overall gain of the amplifier is given by, so VOT divided by VST. So that is naturally can be expressed as, so VOT, okay, this can be, let us express it here. So VOT divided by GVIT into, you can write the ratio over here on the input side and output side. And VOT is VST into GVIT into RL by RL plus R naught. Therefore, it is G into RL by RL plus R naught into GVIT, I'm sorry, into VIT. VOT is that. And what about VST? VST is VIT divided by RI by RS plus RI. Therefore, this can be expressed as Ri. Hence, the overall gain is going to be the gain of the amplifier itself under open circuit output multiplied by these two ratios. So these two ratios, this is going to be the overall gain of the amplifier. Let me use the symbol, so AV here, to indicate gain of voltage gain. So this is because of the division here and the division here. If the gain of the amplifier is actually 100 under open circuit conditions, if there is going to be a half here, an attenuation and a drop in voltage to half here and a drop in voltage to half here. Overall gain is going to be 100 into half is going to be 25. Okay. So in order to get large gain in an voltage amplifier, we want R naught to be much smaller than RL and Ri to be much larger than Rs for the voltage amplifier. Therefore, for the voltage amplifier, these are the desirable things. That means output impedance should be much smaller than the load resistance and the input impedance should be much larger than the source resistance. It's clear? So we shall continue the classification in the next class.